Good afternoon, everyone. First of all, I would like to thank the organizers for giving me opportunity to present my work here, and I would also like to thank ICTS for their nice hospitality. Today, I will be talking about our recent work that dark matter production during reheating. So that has been done in collaboration with Professor Devtosh Choudhury. So this is roughly the plan of my talk. First part of the talk, I will discuss the thermalization of high energy particles that are produced from a metastable field. And in the next part, I'll talk about dark matter production. So before going into the part, first I will discuss that this X-ray image of bullet cluster, this gives us the strongest evidence for the presence of dark matter. And this Planck observation tells us that dark matter shares almost 28% energy budget of the total universe. So now I'll go briefly into the cosmic history of the universe. As you all know, like in the very early stages of its evolution, the universe undergoes through a period of superluminal expansion, during which the universe expand exponentially and inflation drives everything away. But if you see our today's universe that is full of stars and galaxies, so something happened after inflation. Basically, what happened like after inflation, universe reheat, and I'll be mostly interested in dark matter production during this reheating epoch. In the next slide, I will discuss what you mean by reheating of the universe. Basically, in field theoretic language, the basic idea behind reheating is that a metastable field that like dominates the energy density of our universe after inflation, and that field dissipates its energy by producing high energy particle. And in standard cosmological scenario, the basic assumption is that these high energy particle instantaneously thermalize and form a thermal bath, and that is the onset of our radiation domination epoch. So there are works which consider stable relic production during reheating, and this relic density of dark relic that produced during reheating depends on the detailed dynamics of the reheating. For example, the maximum temperature attained by the universe during reheating. But the main thing is that if you consider the production from the thermal bath, you cannot produce dark matter having mass greater than the maximum temperature of the universe. Now, as I discussed earlier, like these recent works, they have assumed instantaneous thermalization of the decay products. But recently, like there have been questions on this assumption: is this a valid assumption or not? So there are a couple of works they have focused on this non-instantaneous thermalization with a constant dissipation rate. But what we did in this work, we have studied the thermalization of this high energy particle in presence of a time varying dissipation rate. We parameterize our dissipation rate like this, where this gamma naught is the time independent part of the dissipation rate, and A end is the scale factor at the end of inflation, and this K1 is some index that will vary in like specific model. So before going into my result, I will briefly discuss what you mean by thermalization. Basically, what happened like after inflation, a metastable field that decay, and the decay products, those are highly energetic and less populated compared to their thermal counterpart. And their phase-wise distribution, the main important point is that the phase-wise distribution of this high energy particle, they differ significantly as compared to their like thermal distribution. And for like to reach into a thermal equilibrium, these particles have to redistribute their energy and produce new particle. And that thermalization proceeds basically via this 2 to n scattering. Now, if you consider this, the minimum n is equal to 2 to 2 scattering, via this 2 to scattering, the particle only redistribute their energy. Now, you can also consider like 2 to 2 annihilation process, but that process rate is very slow, so that which delays the thermalization. So, but this 2 to 2 scattering, they don't contribute for achieving chemical equilibrium because they don't produce new particles. So for reaching this chemical equilibrium, we need to consider this 2 to 3 scattering. Now one can consider this 2 to 3 scattering as like 2 to 2 scattering, and then the 1 to 2 splitting, where these final state particles split into nearly collinearly into 2 daughter particles. Now if you consider this like soft splitting kind of thing, in these cases, whenever your like the formation time is larger than the time for the elastic scattering, then basically what happened, this particle like they experiences multiple scattering before their formation, this daughter particle. Then there will be a destructive interference effect known as the Landau-Pomeranchuk-Migdal effect. This Landau-Pomeranchuk So now I'll consider this dark matter production, but whenever you have your cross section has a strong UV dependence, that basically significantly enhances the dark matter production during reheating epoch. So now what happened, like if you see, since we are considering non-instantaneous thermalization, what happened, like before thermalization we have non-thermal particle, after thermalization we have non-thermal particle. Non-thermal means that the phase distribution differs from the thermal distribution, and after thermalization we have both non-thermal and thermal particle. So now these are basically production mechanism for dark matter, and we have taken this production cross section like this. This M is some mass scale. These are our results. Basically, what we found that if we have only the thermal production, like production from the thermal bath, then in all these cases, these are scenario. This is for some K1 is equal to 3. This is for K1 is equal to 3 half. This is K1 is equal to. This is for K1 is equal to 3 half, and this is K1 is equal to 0. Now, if we only have this thermal production, then like this right hand side of this this line, this is forbidden if you consider only the thermal production. But whenever you have this non-thermal channel, then like you can produce dark matter with mass greater than the maximum temperature of the universe. And these plots are for n is equal to 0, and this is for n is equal to 2. But the main point that we get, like when you consider like a constant dissipation rate, like the dark matter produced before thermalization, like they contribute significantly when your dark matter mass is close to the mass of the like decaying particle. Is same for n is equal to 2 case also, like the dark matter produced before thermalization that contributes significantly into the dark matter relic density. And finally we compare like the various production mechanism, like the dark matter relic produced from the various channel. Here this blue region indicates that like the dark matter produced from conclusions. Thank you.
You lost some time. You can read it out.
Okay, so what we basically in this work we investigate the impact of a time-dependent dissipation rate on the thermalization of high energy particles, and what we found that like decay product takes shorter time for non-zero K1 as compared to the like 0 case, or when the dissipation rate is constant, and the dark matter having mass larger than the maximum temperature of the universe can be produced from the non-thermal channels. And in the temperature decreasing scenario, means in case K1 is equal to 0 scenario, what we found that like the dark matter produced from the before thermalization that dominates in the regional dark matter mass close to the M5 by 2. M5 is the mass of the decaying particle.